Hello everyone, I'm Ruhi and welcome back to another episode of Cross Section. Today, we'll be exploring something that's so common around us, something that we generally tend to associate with maybe dust or dirt, but that something has an amazing science behind it. You ready to know what it is? Let's go. You slowly open your eyes. Your vision is blurry, all you can see is sand. You blink a few times, and the world slowly comes into focus. An endless stretch of beach, palm trees swaying in the distance, the sound of waves gently rolling onto the shore. You slowly sit up, your head pounding. Wait, just a few minutes ago, you were thousands of feet above the Pacific Ocean. Now, you lie on a deserted island? How? Then the memories come rushing back. The warning lights, the engine sputtering, the radio filled with static, the emergency landing that never quite went according to plan. You had been flying alone to a remote research station when your small aircraft was forced down over the ocean. Somehow, against all odds, you survived. You quickly check yourself for injuries. A few cuts, a bruised shoulder, nothing serious. And then you spot your backpack, half buried in the sand. Inside, you find an empty water bottle, a notebook, a camera, and not much else. You slowly scan the horizon. No buildings, no roads, no smoke, no sign of another person. Stretches as far as you can see, but drink it and you'll probably make things even worse. You begin thinking, maybe I can desalinate the water. You look around. No stove, no metal container, no distillation setup. Not happening. Maybe I can build a solar still. Possible, but it'll take hours. And you're so exhausted. So you decide to conserve your energy and continue searching the next morning. The next morning, before the sun has fully risen, you head deeper into the forest. The air feels cooler, everything is quiet. Then something catches your eye. Not because it's moving, because it's sparkling. A giant spider web. Every strand is covered in tiny droplets that shimmer in the morning light like hundreds of miniature diamonds. Most people would admire it for a second and keep walking. You don't. Because right now, those aren't dewdrops. They're water. You carefully run your empty bottle along one edge of the web. A few droplets slide inside. Not much, but enough to make you stop. You look around. Another web, then another, then another. Suddenly, the island looks completely different. You're not seeing spider webs anymore. You're seeing tiny water collectors. Wait, could spider webs actually be collecting water from the air? You spend the next hour collecting as much water as you can. It's nowhere near enough to survive forever. But it's enough. Enough to keep searching. Enough to buy another day. Enough to stay alive. For now. Then you hear something, a helicopter. You sprint toward the beach, waving your arms as high as you can. For a few agonizing seconds, nothing happens. Then the helicopter begins to turn. It has seen you. You're going home. As the helicopter climbs higher, you look down one last time. The morning sun is lighting up the forest. And everywhere, spider webs sparkle like silver threads woven through the trees. You survived! But strangely, it isn't that island that you keep thinking about. It's those spider webs. Weeks later, you're back in your lab. Life has returned to normal. The cuts have healed. The plane crash is now just another story to tell. But one question refuses to leave your mind. How could a thread thinner than a human hair collect water so efficiently? You decide to find out. Your first idea seems obvious. Maybe the spider silk simply becomes colder than everything else. A colder surface would condense more water vapor. Simple, mystery solved. Or so you think. You pull up the photographs from the island. The leaves have dew, the branches have dew, even the rocks have patches of moisture. Everything cooled down overnight. Everything collected water. Yet, the spider silk collected far more. So, temperature couldn't be the whole story. Back to square one. Another idea strikes you. Maybe it's the silk itself. Perhaps spider silk is made from a material that naturally attracts water. Fortunately, that's something you can test. You stretch four different fibers across identical frames: spider silk, cotton thread, a nylon fishing line, and an ordinary sewing thread. You place them inside a humidity chamber overnight. The next morning, every single fiber has collected water. Interesting. So, collecting water isn't unique to spider silk. But then you notice something. The droplets on the cotton appear randomly. The droplets on the nylon also appear randomly. Some merge, some fall, some stay exactly where they formed. Completely disorganized. The spider silk, however, looks different. Its droplets almost seem organized, perfectly spaced. Almost as if the thread knows exactly where each droplet is supposed to go. And that's why maybe the material isn't the entire story. You've run out of ideas. Whenever scientists reach this stage, they usually do one thing. They stop looking around and start looking closer, much closer. You place a strand of spider silk under a scanning electron microscope. At first, it looks exactly like what you expected. A thin thread, nothing unusual. You increase the magnification. Still nothing. One more click, and suddenly, the mystery changes completely. The thread isn't smooth, not even close. Instead, you see a repeating structure. Thicker spindle shaped regions connected by incredibly thin sections of silk. You've never seen anything like it. But seeing the structure isn't enough. You've got to know whether that structure can actually change the way water behaves. So you decide to repeat the experiment. This time, you place the spider silk inside a humid observation chamber and examine it under an optical microscope. Unlike the electron microscope, this lets you watch the wet silk in real time. You begin observing. Tiny droplets start appearing along the thread. At first, they seem completely random. Then, something incredible happens. The droplets begin to move. Slowly, almost imperceptibly, they travel along the thread. And one by one, they gather around those thicker spindle like regions. You lean back in your chair. So, it wasn't just the material, it was in fact the architecture. But that question, right there, creates an even bigger mystery. Because a water droplet doesn't know what spider silk is. A water droplet doesn't know where to go. It simply responds to the forces acting on it. Why does it consistently move towards those particular regions? What is the silk doing to the water? Now we know what happens. Tiny droplets appear all along the thread, and somehow all of them start moving towards those bead like structures. Wait, why is this happening? Hold on. Before that, we have a surprise. Those bead like structures weren't always there. When the spider first spins its web, the thread actually looks very different. Instead of tiny beads, it's covered in fluffy tufts made of thousands of microscopic fibers. Imagine a paintbrush. When it's dry, the bristles spread out and look fluffy. Dip it into water, and those bristles clump together into tight bundles. Spider silk behaves in a surprisingly similar way. As water begins condensing, those fluffy tufts slowly collapse. forming the bead-like structures we saw under the microscope. Scientists call this process wet rebuilding. In other words, the water doesn't just collect on the spider web, it actually transforms the web into a better water collector. And now, those bead-like structures are finally ready to do their job. If you liked the video till now, subscribe for more content like this. Where spider silk behaves in a really clever way. At first glance, the thread appears almost the same, but zoom in and you'll observe two distinct parts. And what's more, these distinct parts have different functions. Imagine rain falling on a mountain. At first, tiny streams appear everywhere. As they flow downhill, they merge together, forming larger and larger streams, until eventually they become one river. The spiderweb works in much the same way. Tiny droplets first appear all along the thread. The thin sections of the thread, called joints, keep collecting new droplets from the humid air. The thicker bead-like section, called spindle knots, act as collection points. The droplets don't stay where they first formed. They slowly travel toward the nearest spindle knot. When they arrive, they merge with the droplets already waiting there. Many tiny droplets become one much larger droplet. And because the joints are now clear again, they can begin collecting more water. The process repeats again and again and again. The spiderweb isn't just collecting water, it's moving it. That still does not answer the question of why exactly the water droplet is moving. So let's definitely do that now. And the answer comes from two surprisingly simple tricks. Let's zoom in one last time. The spindle knot isn't just thicker. Its surface is also much rougher. Under the microscope, it looks like thousands of tiny fibers pointing in different directions. The joints are different. Their fibers run neatly alongside each other, making them much smoother. Why does that matter? Imagine placing a drop of water on two different surfaces. On one, the drop barely sticks. On the other, it spreads out and clings more strongly. Water interacts differently with each surface. Scientists describe this using something called surface energy. The spindle knot has a different and effectively higher surface energy than the joint. That makes the spindle knot more favorable for the water droplet. So, the droplet has a reason to move toward it. But that is only half the story. Another look at the thread. The spindle knot isn't just rougher, it's also thicker. And believe it or not, that tiny difference in thickness changes the pressure inside the drop itself. Scientists call this Laplace pressure. You don't need to remember the name. Just remember one simple idea. A droplet wrapped around a very thin thread experiences a higher pressure than one wrapped around a thicker thread. Since the joint is thinner, the pressure there is higher. The spindle knot is thicker, so the pressure is lower. And just like air naturally flows from a region of high pressure to low pressure, the pressure difference drives the liquid towards the spindle knot. The surface energy gives the water droplet a preference. The Laplace pressure gives it a direction. One final obstacle. Tiny droplets are stubborn. They love sticking to surfaces. Sometimes they stick so well, they refuse to move at all. Scientists call this contact angle hysteresis. Think of trying to push a heavy box across a floor. The hardest part is getting it to start moving. Water droplets face a similar problem. Their contact line can become pinned to tiny imperfections on a surface. So even when a force is trying to move the droplet, it may stay exactly where it is. Here's what makes spider silk so remarkable. The spindle knot creates a surface energy difference. The change in curvature creates a pressure difference. And together, these two effects are strong enough to overcome the droplet's resistance to motion. Neither the surface energy nor the Laplace pressure would be enough on their own. But combined together, they have enough force to overcome that contact hysteresis, and then they create something extraordinary: the movement of that water droplet. A thread thinner than human hair can collect water from the air, guide it exactly where it needs to go, and repeat the process over and over again. What have we actually discovered? A spider web doesn't collect water because it's made from some magical material. And it certainly is not because spiders understand physics, obviously. It's because nature, through millions of years of evolution, solved a problem that we, as engineers or scientists, are discovering right now. First, it creates tiny droplets. Then, it guides those droplets exactly where they need to go. And finally, it gathers hundreds of tiny droplets into one large drop. No batteries, no pumps, no moving parts, just the architecture of a thread. And once engineers understood that, they began asking a fascinating question. What other problems could this solve? The problem was obvious: fresh water. Nearly 2 billion people around the world experience water scarcity for at least part of the year. But here's the strange thing. In many dry regions, the air still contains water. Not liquid water, water vapor, invisible but everywhere. The challenge isn't finding water, it's turning that invisible vapor into liquid water efficiently. Sounds familiar? That's exactly what the spiderweb had been doing all along. So engineers designed artificial fibers and fog harvesting meshes inspired by spider silk. Just like the web, they encourage tiny droplets to form, guide them together, and collect them into larger drops that can be harvested. Nature had already solved the problem. Engineers simply borrowed the solution. The problem wasn't about collecting water, it was about moving it. Now imagine trying to move a droplet smaller than a grain of sand. Normally, you need tiny pumps, tiny valves, tiny motors. But the spider web showed us something remarkable. If you shape a surface correctly, the droplet moves on its own. No external force, no moving parts, just physics. Today, that same idea is inspiring microfluidic devices, lab-on-a-chip systems, and medical diagnostic devices, where tiny droplets need to travel with incredible precision. Instead of pushing the droplet, engineers simply guide it, exactly the way the spider does. Next time you walk outside on a cool morning and sunlight catches a spider web, don't just see a few drops of dew. See a tiny engineering masterpiece, a thread that rebuilds itself when it gets wet, collects water from the air, guides every droplet without a pump, and quietly demonstrates ideas that engineers are now only learning to recreate. Sometimes, the greatest engineering breakthroughs aren't hidden inside billion-dollar laboratories. They're hanging silently between two branches, waiting for the morning dew. And that brings us to the end of this video. It's amazing, isn't it? How such simple things we see around us every day can actually have such complex mechanisms behind them. If you like this video, do like it and do share and subscribe. Looking forward to seeing you soon. Also, if you have any comments or suggestions or feedback, do drop them in the comment section below. See you next time.